Early one morning, in the year 43, 4 legions of highly trained Roman soldiers stood on the northern shore of what is now France. 4 legions, that's 20,000 men. They had horses and siege equipment, they even had elephants. Together, they looked out across the English Channel. The fog obscured the horizon. This was the very edge of the Holy Roman Empire. This incredible fighting force boarded a fleet of ships and invaded Britannia. After 4 years of overwhelmingly lopsided fighting, the entire southern half of the island was claimed in the name of Emperor Claudius. Claudius is one of the emperors you don't hear a lot about. Now, you probably know Caligula. He was the insane one, that vicious killer, that sexual deviant. And I know you've heard of Nero. He's the guy that fiddled while Rome burned. Well, Claudius ruled for the 13 years in between those two. Once the fighting was done and the savages were subdued, Claudius's troops started trying to change the culture there, renaming the cities with Latinized names and building temples. And in the city they called Camulodunum, they built the grandest of them all. It was called the Temple of Claudius, and it was the largest in all of Britannia. The Temple of Claudius was a marvel of engineering at the time. The foundation, or podium as it was called, was built by digging trenches and then filling them with mortar and crushed rock. That is a really primitive but really solid form of concrete. There were 28 ornate columns outside made of curved bricks covered in plaster. There were beautiful gardens and a stone perimeter wall for defense. The temple itself, well, it was more imposing than beautiful. The walls stood more than 65 feet high, and they were faced with polished marble brought all the way from North Africa. The entire building had no windows. It took 10 years to build, and it was completed just in time. In the year 60, a tribe of Britons began a revolt against the Romans. Camulodunum was their first target. They stormed the town and won swift battles against the Roman garrison. These were not the bold legionnaires that had crossed the Channel 17 years before. These troops were old and fat and lazy. They were the ones that got left behind to collect taxes. The survivors ran to the temple to hide. It had been built as an homage to the glory of Rome, but now it served as their last chance for survival. The tall, windowless walls and giant brass doors provided them a safe haven. But after a 2-day siege, the Britons forced open the doors and killed everyone inside. Victorious, the Britons tore down the temple and all the other Roman buildings in town. They toppled the columns. They stripped the marble until all that remained was the foundation, that concrete base. Over the next 1,000 years, the town changed its name from Camulodunum to Colchester, and by 1076, it was time to build a proper castle. They chose a spot on a hill with commanding views of the surrounding countryside, and imagine their excitement when they realized that there was already a foundation there. It was 1,000 years old, but still solid rock, already in place. It was the podium of the old Roman temple. The castle they built was historic. The keep, that's the central building, has the largest area of any medieval tower built in Britain or anywhere in Europe for that matter. 200 years later, a group of English barons, with the support of the French, started a rebellion against King John. As a result, a contingent of French soldiers found themselves defending Colchester Castle from the British. Thanks to the strength of the castle, 116 French militiamen were able to hold off the army of King John for 3 months. Ultimately, a truce was called. The English got the castle, but the French were allowed to leave safely. Centuries passed, And castles, well, they fell out of fashion. They were expensive to maintain and they weren't really needed for defense. Then, someone figured out that the same construction design that made it great for keeping enemies out would make it great for keeping enemies in. So, Colchester Castle became a jail. It was used to imprison and interrogate suspected witches. And during the Second English Civil War, the leaders of the Royalists were executed there. In fact, there's a spot out back where they were buried, and to this day, they say, no grass grows there. Eventually, the land was sold to a private owner, and then to another, and then to another, until in the late 17th century, they decided to tear down what was left of the castle and sell the stone as construction material. They used giant mechanical screws to separate the blocks, and gunpowder to blow apart the mortar, but it wasn't enough. This medieval castle, built on the podium of a Roman temple, was too much for 17th century demolition techniques. So, if you go to England today and decide to visit a small town 50 miles northeast of London, you'll find a sturdy stone building on that very site. The building that was used to keep Roman soldiers safe from the Britons, French soldiers safe from the English, and townspeople safe from witches and rebels is now a museum, keeping all of us safe from ignorance, perhaps. It's where the good people of Colchester protect and preserve Roman artifacts for visitors from all over the world to enjoy. It's definitely worth a visit, and when you go, you'll see firsthand how each generation used what the previous one had built to make something altogether new. I'm Dan Riskin, and this is Inside the Breakthrough, how science comes to life. This series is about research, that driving desire to learn new things, answer new questions, and make the world a better place. Specifically, in this episode, I'm looking at how research done many years ago laid the foundation for modern scientists.
Today's achievements began in the far, far distant past, when the Earth was shrouded in the mists of ignorance and fear.
I want to trace a map of the route we've taken from the past to the present.
The achievements of men of science pyramids, laying the foundations for new and greater industry, and a prosperity that reached to every town and village and farm.
But it wasn't a straight line, or even a pyramid as those 1950s newsreels suggest. It was, well, to use a term that also originated in Britain, a long and winding road.
And still the need for further development marches on.
This podcast is produced by a research group in Manitoba, Canada. The company is called Scimar, and the man behind it is Dr. Wayne Lott. Later in this episode, we'll hear from Dr. Lott about what research served as the foundation for their work. But first, a campfire story. It's a warm summer night, and a family of 4 is enjoying a fire beside a lake.
Boy, just look at those stars. You almost feel as if you could touch them.
The boy, a teenager, turns to his father.
Do you suppose we ever will?
Will what?
Oh, reach the planet, the moon, space travel.
No doubt about it.
So that was 1955, and that dad was right. He even threw in this little bit of wisdom.
Oh, maybe it'd be a long time before we reach the planets. They're pretty far away.
Yeah, the planets are pretty far away. That's why it's taken us so long to discover them. You might even say it's taken generations. In ancient times, stargazers identified Mercury, Venus, and Mars. Those are the terrestrial planets, the ones that are closest to the Sun and also to Earth. Jupiter and Saturn were also put on the map in prehistoric times. Those planets stood apart from the stars because they moved. If you look at the sky night after night, the stars are all in fixed positions relative to one another, like a giant sphere around us that rotates but never changes. The planets move, though. Their positions relative to the fixed stars change. And that's how humans knew from very early on that there was something special about them. In fact, the word planet comes from the Greek word meaning wanderer. Now, for centuries, we knew about those 5, well, 6 if you include Earth, and that is all. Eventually, we got telescopes, but still no new planets. Stars? Sure, we had lots of those. John Flamsteed, England's first ever astronomer royal, catalogued more than 3,000 of them, including one called 34 Tauri. Why do I mention that one? Well, Flamsteed recorded it in 1690. Then, about 100 years later, William Herschel, the first ever president of the Royal Astronomical Society, looked at 34 Tauri and said, "Oh, you know what? I think that's not a star. I think it's a very slow comet." That's my accent of a person born in Germany who then moves to England at the age of 19 and is very good on the cello. Anyway, he watched it for a few more months and then he says, no, wrong again. It is a planet. And that is how we got our seventh planet, Uranus. But this is not the story of Flamsteed and Herschel, and it's not the story of Uranus. This is the story of what Uranus taught us. You see, that giant greenish-blue ball of cold gas takes 84 years to go around the sun. And that means that unless they started when they were babies in diapers, no single human can actually track its entire orbit. It has to be done by a series of astronomers, each one recording its position and then passing on their observations to their colleagues over more than 8 decades. And just 60 years into that effort, before we even had one full revolution in the books, a French astronomer named Alexis Bouvard noticed that something wasn't right. Uranus was wobbling. So here's the thing. Bouvard was 14 years old when Uranus was discovered. Over the next 55 years, he tracked its movement through the sky. Now, if you're a young, good-looking, educated person living in 18th century Paris, you could probably find something a little more exciting to do with your evenings than plotting the location of a tiny speck of light. But that was Bouvard. That's what he wanted to do. And he wasn't even looking for anything in particular. He was just plotting its path and comparing the observations with the predicted path based on where Newton's laws said it should go. And that is what Bouvard did, night after night after night. A planet revolves around its star in a very predictable pattern, and we know that because Sir Isaac Newton came up with the law of gravity and based on that equation wrote up the laws of motion. Gravity is a force that pulls two objects toward each other. It's what pulls an apple to the Earth, and it's what holds a planet in a predictable orbit. Newton's laws say that the magnitude of that force is determined by each of their masses and how far apart they are. Those laws became cornerstone tools for understanding how planets move.
Now, as the science developed and measurements were made ever more accurately, the tests of Newton's law became much more stringent.
That is Richard Feynman, one of America's most famous physicists. He worked on the Manhattan Project, building the first nuclear bomb. He won a Nobel Prize, and he was brought in to analyze the space shuttle after the Challenger disaster. And like he said, Newton's laws, no matter how much data you threw at them, always held up. You just had to be sure to enter all the masses that are close enough to pull on the object. This is how Feynman explains it.
The planets shouldn't really go in ellipses because, according to Newton's laws, they're not attracted only by the sun, but also they pull on each other a little bit, only a little bit, but a little bit is something, and will alter the motion a little bit.
That little bit is exactly what Bouvard noticed during those long, lonely nights in Paris.
It was noticed that Jupiter and Saturn went according to the calculations, but that Uranus was doing something funny.
Yeah, Uranus wasn't following the rules. It was dancing a little, which is what other people would have been doing with those starry nights in Paris. And maybe Bouvard should have been doing more of that, because life is short. In fact, just after noticing that Uranus was misbehaving, Bouvard died. Yeah, you spend your whole life plotting coordinates on the slowest moving planet known, and you finally find an irregularity, and then you keel over. That is a tough break. But not to worry, other members of the scientific community were there to pick up where he left off.
Two men, Adams and Leverrier, independently and at almost exactly the same time, proposed that the motions of Uranus were due to an unseen as yet new planet.
Adams was John Couch Adams, a Brit. Leverrier was Urbain Le Verrier, a Frenchman, and they both wrote up their theories and sent them to observatories. First, Adams, the Brit.
Turn your telescope and look there and you'll find a planet. How absurd, said one of the observatories, that some guy sitting with pieces of paper and pencils can tell us where we'd look to find some new planet.
Those stuffy jerks wouldn't even look. So Adams' discovery went nowhere. Le Verrier, meanwhile, sent his coordinates to the observatory in Berlin.
The other observatory was the administration was different. And they found the Neptune.
Yeah, they found Neptune. It's the only planet discovered through calculation rather than observation. Le Verrier told the world that he had found the 8th planet of our solar system not in the night sky, but rather à la pointe de sa plume, at the tip of his pen. But the truth is, he didn't find it himself. It took John Flamsteed, William Herschel, Alexis Bouvard, Urbain Le Verrier, and a guy named Johann Galle, who just happened to be on duty that night in the Berlin Observatory. It took generations. A couple of years later, Le Verrier was back at it again, and this time he was looking in the other direction, at Mercury.
It became apparent that the motion of the planet Mercury was not exactly right.
Just like Uranus, Mercury had a wobble.
And this caused a lot of trouble and had no explanation.
Le Verrier followed the same playbook that had led to the discovery of Neptune. He took the observations of Mercury's actual orbit, and he took everything they knew about how the sun and the other planets should affect its movement, and he used Newton's laws to solve for what was missing. The result was the discovery of another new planet. Once again, he had discovered a planet not in the night sky, but at the tip of his pen. It was smaller than Mercury, and Mercury is not big. In fact, Mercury is smaller than our moon, so this thing was tiny. And its orbit was even closer to the sun. A planet with that orbit would have to be scorching hot, a planet on fire. So it was given the name Vulcan.
Dan? Sorry, Vulcan isn't a real planet. That's just from Star Trek. That's where Mr. Spock is from.
No, Vulcan was real. To the people of that time, it was every bit as real as Neptune. Hear me out on this. Le Verrier sent the coordinates of where it should be found to a handful of observatories and asked them for visual confirmation. They'd learned the lesson from Neptune, so they all looked. But none of them could find it. Now, that wasn't altogether unexpected. I mean, think about the layout of the solar system. If you're looking for a planet out beyond Uranus, that means pointing your telescope outward at night and looking for sunlight bouncing off a distant object. The lighting is perfect. Looking for Vulcan requires pointing your telescope toward the sun during the day and looking for a tiny rock that's very close to it and does not emit its own light. There's no reflection. At best, you're looking for something that's a silhouette as it passes in front of the sun. Now keep in mind, Urbain Le Verrier was a legend, the most celebrated astronomer of his time. He is the only person in history to discover a planet using math. And his calculations were based on Sir Isaac Newton's laws of motion. And those are also untouchable. They've been proven correct time and time again. There was no doubt in anyone's mind that Vulcan was there, we just needed better equipment to see it. Eventually, Le Verrier dies, like Bouvard and Herschel and Flamsteed before him. He dies in 1877, and at the time, he is remembered as the man who discovered the most distant planet in our solar system, Neptune, and the innermost planet, Vulcan. When the Eiffel Tower gets built 10 years after his death, Le Verrier's name is engraved on it. That is the highest honor available to scientists, engineers, and mathematicians in France. The only minor blemish on all of his findings was, well, no one could find Vulcan. But telescopes were improving every year, so surely visual confirmation was coming soon. It's 1915, almost 50 years since Vulcan's existence had been proven mathematically, and still no one has seen it. The job of explaining the wobble in Mercury's orbit has fallen to a new generation of scientists. In particular, an up-and-comer named Albert Einstein. Einstein took Newton's laws, which were universally revered, and asked, do they still apply in the most extreme circumstances? What he found is that with really massive objects like stars, the space-time relationship gets bent, it gets warped, and that means that the calculations change.
Through this hypothesis, time and space are robbed of the last trace of objective reality.
Lots of modern teachers have tried to explain this by saying it's kind of like putting a bowling ball in the middle of a trampoline. It bends the shape of the trampoline and affects the movement of a marble being rolled across it. So if you try to roll it straight, the path bends. It's worth noting, however, that Einstein never actually referred to a trampoline or a bowling ball or a marble in any of his papers. Instead, he talked about the Sun and Mercury.
A point mass, the Sun, is located at the origin of the coordinate system. The gravitational field this point mass produces can be calculated from these equations by means of successive approximations.
You see, the general theory of relativity, that's what Einstein called his discovery, isn't just one equation that you plug everything into once. The way you use it is to run the numbers, get an approximation, and then run them again to get a better answer, and do this over and over, each time making your result more accurate.
The calculation yields, for the planet Mercury, a perihelion advance of 43 seconds per century as the unexplained difference between observations and the Newtonian theory.
Einstein's new theory perfectly predicts Mercury's orbit. The planet was following the rules, we just didn't know the rules until Einstein figured them out. And a lot of people think of Einstein as this singular genius who came up with all of this by himself, but that's not true. In his own paper, he has two lines that give a more complete picture. First,
it explains qualitatively and quantitatively the secular rotation of the orbit of Mercury, which was discovered by Leverrier.
Keep in mind, Urbain Le Verrier has been dead more than 40 years at this point, but Einstein still acknowledges that it's his observations that form the foundation for this work. And he finishes his paper with this gem.
However, I prefer to relinquish a final decision to the astronomical specialists.
Yeah, after pages and pages of equations, he still says, let's turn it over to the folks with the telescopes to see if this really works. He builds on the past and he sets a foundation for the future. Einstein's papers were a triumph for science, but sadly, they were a death blow for the planet Vulcan. The planet that had been discovered at the tip of Le Verrier's pen ceased to exist thanks to the tip of Einstein's. That is one of my favorite science stories of all time because it's a mix of abstract thinkers and in-the-field researchers. And also, it connects a dozen brilliant people from Newton all the way to Einstein, each one building on the work of those that came before them. This is the part of the show where we pivot from historical stories to a modern one, the story of Scimar. Scimar is a modern medical research company. What they do and how they do it would have baffled and amazed people like Le Verrier, Bouvard, and Herschel. Even Newton and Einstein would be blown away by what happens in a modern lab. But some things haven't changed. One constant is the importance of building on the work of your predecessors. Just as with Colchester Castle or the discovery of Neptune, we're going to start at the beginning with the first diagnosis of diabetes.
There are recorded instances of diabetes from almost 3,000 years ago.
That's Dr. Wayne Lott, the founding researcher at Scimar.
Diabetes was originally diagnosed by tasting the urine. Diabetes mellitus is typified by large volumes of sweet urine, and that's a different disease from diabetes insipidus, where it's large volumes of urine that isn't sweet.
Dr. Lott also learned from more recent scientists.
I'd have to say that Ernest Starling back in the late 1800s is one of my absolute heroes. This guy had to be crazy to have done all of the different things that he did and to come up with the ideas that he did, simply measuring blood flow in an artery.
Starling measured the flow of blood by sticking a tiny hair into an artery and measuring how much it bent.
Starling did a lot of stuff like that. He actually was the discoverer of the first hormone and was able to show how you had to demonstrate the functions of a hormone being released from one organ and acting on a different organ. So that would be, my scientific hero.
It's no surprise that the guy who discovered the first hormone holds a central place in Dr. Lott's work. After all, diabetes research is always focused on a hormone from the pancreas, insulin. And Lott is building on that by utilizing a second hormone, something called HIS, hepatic insulin sensitizing substance. HIS has the potential to change the way we diagnose, treat, and someday even reverse type 2 diabetes. But it has taken 30 years to get to this stage. And well, Dr. Lott is not a spring chicken anymore. He's 74 years old. That is almost a full orbit of the planet Uranus.
I don't really like the idea of slowing down. When I go out, I want to be going so fast I skin both knees on the way out. If I don't make it for supper, well, first off, our team is already able to carry this forward. There's no question about that. But the idea of not finishing anything, nothing is ever finished.
Nothing is ever finished. That's a good motto for any great scientist. Science isn't a straight line. It moves forward in fits and spurts, but it does keep moving. There may be long periods of time where everyone involved says, yeah, we've got this nailed down. We know all there is to know about this. But then, all of a sudden, things pick up and move again. I mean, for 50 years, everyone agreed there was a planet Vulcan. And it's those periods of time, the stagnant parts, that Lott finds problematic.
I've always been concerned about plateaus. I like the acceleration of a learning curve. And as long as the effort that I'm putting in leads to an acceleration in the accumulation of knowledge or experience or whatever, then I'm willing to just put in as much energy as I possibly can.
But in science, the effort you put in isn't always matched by the output.
When I hit a plateau and I'm still putting in the same amount of energy and I'm not moving the needle forward, that's when I have typically bailed out and move over to something else.
What he's talking about is not beating your head against a wall. Instead, recognizing that sometimes a problem requires a new approach, a new technology, or even just a fresh set of eyes. Even if that takes the wisdom of a future generation. Next time around, we're going to tackle a thorny, awkward, ugly question. If you made a discovery that could save millions of lives, would you give it away or would you sell it? And before you say that's an easy decision, ask yourself if you're basing your answer on any assumptions. Come back for the next episode and maybe I'll prove you wrong. That's next time on Inside the Breakthrough, How Science Comes to Life. I'm Dan Riskin. Thanks for listening. Oh, one last thing. Researchers continue to track planets and compare their observed paths to their predicted paths, looking for inconsistencies, and they also do projections of what those planets might do in the future as their orbits degrade. See, the sun is burning, so it's losing mass, and as it does that, it's going to start throwing things out of whack. And one of those things is Mercury. Some researchers at the Paris Observatory, that's the same place where Alexis Bouvard spent all those nights alone, ran 2,500 computer simulations to figure out what might happen with Mercury. And in 25 of those, 1% of those, all hell breaks loose. The scariest scenario sees Mercury getting thrown outward because it gets attracted by Jupiter, and that messes up the orbit of Mars, which then has a near miss with the Earth, and then that sends our little blue marble careening inward for a head-on collision with Venus. But don't panic yet. The timeline for that whole scenario is 3.3 billion years from now. So we've got some time, at least a couple of generations.
Join us as we bring science to life. Listen to Inside the Breakthrough with Dan Riskin, streaming now wherever you get your podcasts. Inside the Breakthrough is an innovative podcast for scientists, science lovers, and history buffs. Host Dan Riskin of the Discovery Channel's Daily Planet expertly shares a collection of unusual and fascinating stories from the history of science. The show is produced by Scimar, a research group exploring a paradigm shift in the way we treat type 2 diabetes. Learn how science comes to life with Inside the Breakthrough, now streaming on Apple Podcasts, Spotify, and Google Podcasts.